Okay, YouTube, in this video we're going to focus on how to use an inverse matrix to solve a system of equations. So I think it's actually critical to point out at this point in terms of methods for solving systems. So we say methods for solving systems of linear equations. We're getting quite a few on our list here. So like, we have elimination, okay, elimination, and substitution. These are two. Substitution. We also have graphing. We can see where graphs intersect to find common points that are common solutions, so graphing. And we also have this. We could write an augmented matrix, augmented, and then put it in either REF or RREF. But we could do one of those two things right there to help us solve a system. What we're going to do is we're just going to build one more method onto this. And what we're going to do is we're going to call this matrix equation, solve a matrix equation. And so in order to use an inverse matrix to solve a matrix equation, we have to have this matrix equation in the first place. So the first thing we're going to do is we're going to set up our matrix equation here. And so one thing that I want everybody to notice here is this. We could write two matrices essentially because of matrix equality that say this. We could have 18x plus 12y and 30x plus 24y. And that's a 2-by-1 matrix. It has two rows and one column here. That's technically equal to this matrix over here on the right because we know that two matrices that have the same order that are equal, their corresponding parts are equal. So I can clearly see that this equation on this expression 18x plus 12y equals the 13 and that 30x plus 24y equals the 23. The thing here is we can actually decompose this even further, and what I know is that this matrix right here, technically because of matrix multiplication, I could say that this is 18, 12, 30, 24. And I could take it times this 2-by-1 matrix xy. Okay, and so what I want to point out here is this, and this is kind of hard for people to see at first here. This is a 2-by-2 times a 2-by-1, and all of this, by the way, still equals 13 and 23 in this 2-by-1 right here. But basically, if you were to take this 2-by-2 times this 2-by, and by the way, let me get this out here, this is a 2-by-1, then these inner dimensions match, and what we get is a 2-by-1, which is the exact same 2-by-1 that you're seeing over here. It's just that if I were to write out this matrix here, 2-by-1 on the left, I would say in order to get this entry right here, I would take this first row times this first column. You'll notice that we get 18 times x plus 12 times y, which is precisely what you see in this first row, first column of this matrix. To get the second row, first column, we would take this second row times this first column here. We'd get 30 times x plus 24 times y, and that would come out to equal 23. So I want everybody to see that this system right here can be written as a matrix equation. And so in a matrix equation, what we do is we decompose this system into three distinct parts. And so we're going to refer to this first matrix here as our coefficient matrix. Now we've seen a coefficient matrix before. When we write augmented matrices, it's the part on the left. But the coefficient matrix is this square matrix here that just contains our coefficients. Now, this matrix right here has a name. We refer to this as the variable matrix. And this is a column matrix that will have as many variables as your system has in the first place here. So we had two rows here in a single column with an x and a y. And so now our constant matrix is obtained just by getting these two values right here. And so we refer to this as the constant matrix. So now what I'm going to do is I'm actually going to give these matrices names. And I'm actually going to refer to this first matrix here, the coefficient matrix, as A. I'm going to refer to my variable matrix as this variable matrix x, and I'm going to refer to my coefficient or my constant matrix here as b. So what we end up with is what we call a matrix equation. And this matrix equation, coefficient matrix times variable matrix equals constant matrix, does represent the same system. So what we want to do is we want to find out the values of x and y. So if I were to do this, what we could do is we could just solve for this matrix in this equation right here, get x by itself, and we could say, well, then the matrix x, which is really just this xy, equals some other matrix here where, what if I got like 2 and 1? I could tell you that x and y are 2 and 1 respectively. It's just, the question remains, how do I solve for x in a matrix equation? So here's the hard part. If you have a real number equation and we had something like ax equals b, where these are real numbers, then it'd be easy. What we could do is we could just divide both sides by a, and we'd say that I get x equals b over a, and we'd be done with it. What I can tell you is with matrices, there is no such thing as matrix division. I cannot divide both sides of this equation by matrix A and get a statement that says that x equals matrix B divided by matrix A. It is just not a defined operation. What we do know though is this. We know that multiplication is defined. So we also know that anything times its inverse and no matter what order we multiply gives us the identity. And we also know that anything times the identity is equal to the identity times that thing is equal to itself. So here's going to be our strategy for solving a matrix equation. What we're going to do is this. We are going to multiply on the left-hand side, by A inverse. And so what we end up here is with this. What we end up with is this. We'd say AX equals B. We're going to multiply on the left side by A inverse. So we say the left side, on the left-hand side, multiplied by A inverse times A times X is equal to, now we have to multiply by the left-hand side, or our left-hand side by A inverse over here as well. Remember, it does matter what order you multiply matrices in. So we're going to multiply on the left-hand side of both of these expressions to get this. And what we're going to say is this. We say A inverse times A comes out to be the identity matrix. Identity matrix. And remember what we know about the identity matrix. We know that the identity matrix, anything times the identity matrix, is itself. So what we have here is the identity times X equals A inverse times B. And so we would say that I times X equals X, and we'd say the definition of the identity matrix gives us this. So anything times the identity itself, what we end up with here is this. And so what I would argue is this. With any system that is a square system, we can always write a coefficient matrix times a variable matrix equals a constant matrix, but just by dropping these things in here. And it's always of the form A times X equals B, and we're always looking for X. So we would say that this is the solution to many matrix equations, but especially when we're talking for a system here, right here, okay? So that solution is always going to be A inverse times B. So what I want to show everybody here is this. If we know our coefficient matrix is this 18, 12, 30, 24, and we know that our B here is this 13, 23, then let's take A inverse times B, and we should be able to solve for this X value. So if I know that X equals A inverse times B, let's take a look at this system that we have here. Now what I want to show everybody is that under the matrix menu, this matrix A, if I bring this out, A is already my coefficient matrix here. Excuse me. Matrix B, if we go pull out B, is a 2x1 matrix containing my constants. This is my constant matrix. And so in order to find out what the solutions to the system are, all we have to do is type in A inverse B and we should have them. So we'll say matrix A, inverse key, times matrix B. And I end up with this right here. Now I notice this is a fraction, so I'm going to hit math, fraction, make my answer a fraction. But I get 1/2 and 1/3. So what I'm going to write here is this. I got a 2x1 matrix with a half here and a third here. And I want you to realize that this matrix X in the first place was equal to the variable matrix XY. So because of one-to-one properties, we could just say here that X is equal to a half and that Y is equal to a third. So to recap everything we wrote right here, basically we want to be able to write a system as a matrix equation in the first place, and in order to solve for this matrix right here, what we would do is we would just type in A inverse B, or take the inverse of our coefficient matrix times our constant matrix, and you should always end up with the solutions. Cheers.